Hello, everyone. I want to welcome you to the REYES session today on an introduction to mechanical engineering. My name is Carol Considine, and I'm the Assistant Dean for Outreach and Diversity at Old Dominion University's Baton College of Engineering and Technology. We're really excited to talk to you about the different disciplines that we have at the College of Engineering, and we are very excited to have our speaker today, Drew Landman. I'd like to introduce Drew. He has over 25 years of experience in engineering and engineering education. He spent 13 years as a chief engineer at the Langley full-scale wind tunnel, where he conducted aerodynamic testing on ground and flight vehicles. He also has experience with the design, building, and calibration for instrumentation. He has taught short courses in statistical engineering for over 10 years to the Department of Defense, NASA, and industry. So Drew, thank you for being here today, and please take it away.
Oh, thanks for the nice introduction, Carol. Okay, so I'm going to talk to you about mechanical engineering today. I'm currently a professor and associate chair in the Department of Mechanical and Aerospace Engineering. And let's go ahead and get started here. Okay, so what is mechanical engineering? I'm going to start off with a classical definition, an engineering discipline that encompasses the generation and application of heat and mechanical power and the design, production, and use of machines. So it's a very generic definition, kind of all-encompassing. And first thing we need to understand is, what is a machine? So the picture at the bottom gives us some example where we see machines building machines. All right, a machine is an apparatus using or applying mechanical power and having several parts, each with a definite function, together performing a particular task. So we're all familiar with machines. We drive one every day to work, car, okay? We're using pumps, we're using compressors, we're using wind turbines to generate electricity. We use piping systems every day in our house, pressure vessels, heat exchangers, all under the purview of mechanical engineering. We're also familiar with consumer goods such as televisions, coffee grinders, toothbrushes. Again, they all involve some input from mechanical engineers. In the manufacturing industry, we have material handling equipment such as conveyors and robots and production assembly lines. And that's what you're seeing in the picture at the bottom, an assembly line that's using robots. Finally, we have vehicles, cars, trucks, heavy equipment such as bulldozers and mining equipment, buses, aircraft, and ships. They're all, again, under this general umbrella of mechanical engineering. Finally, we have power generation equipment. We'll focus on that a little bit today with wind power, hydroelectric, nuclear, and geothermal as some examples. So those are the classical elements of mechanical engineering. In more recent years, we've expanded what is included in mechanical engineering to branch out a little bit into the grayer or more blurry areas of other disciplines. So we're now looking at not only mechanical, but a little bit of electrical and a little bit of software as well. And to address that need, we have come up with a secondary series of courses within mechanical engineering, and that area is typically called mechatronics or just electromechanical systems. So in the little diagram at the right, I give you a feel for how that works. So on the left-hand green circle, we see computers, and computers could be under electrical computer engineering. But you can see that the intersection of that green circle with the maroon circle at the bottom for mechanical systems, they intersect in mechanical CAD, because here we're using computers to do computer-aided design of mechanical systems. On the right-hand side, we intersect with the purple circle in electronic systems, and here we have electromechanics. So when we look at something like a robot, it involves mechanical parts or machine elements, but it also involves things like motors and control systems, which are electronic parts. So you can see how we have this intersection of the disciplines. So in the center there, we label this mechatronics. So more and more these days, we need to be able to do all of these jobs. Another topic that we're addressing more and more, particularly in the research and development side of things, is this idea of making precise measurements understanding what is the uncertainty associated with these measurements. And that's not only in experiments that involve physical systems, but also in computer simulations. So we have added a course to the undergraduate curriculum in probability and statistics. So let's start off with some typical jobs of a mechanical engineer. We mentioned consumer products. So product design is one big area. So this could be designing products that would be something we're familiar with, like a bicycle or a car, but it could also be something like a knee replacement. And there's actually some work being done in that area at Old Dominion University. Could be internal combustion engines, could be drones, right? Appliances at home. These are all products that we use and that have to have some aspect of mechanical engineering. Research and development. So here we're researching new ideas and solutions that satisfy society's demands, or maybe we're improving or expanding on older ideas. So my example there is given by the picture of the 2020 Mars rover. So here's something that we have some data on. We've put Mars rovers on Mars before, but we have new ideas. We have new science, right, that has to be included. So this is an area for research and development. Manufacturing. So I mentioned designing and building machines. We're using machines to design and build machines, right? So we have multi-layers of machine design within manufacturing. And this is going to fall into mass production of consumer products for sure. And then systems management might be looking at the management of a large system, like a manufacturing facility or maybe a power plant. Energy falls closely under systems management because we're looking at how energy is created, stored, and moved in industries that produce and deliver electrical power. So this could be the natural gas, oil, or alternative energy industries. So let's start off with a wind power example, something right out of energy. What I've done with these slides is I have put in bold text, relevant coursework from the undergraduate curriculum in mechanical engineering. And this is not necessarily Old Dominion University centric. This is going to be really any mechanical engineering undergraduate program. Okay, so what you see in the picture there is a offshore wind farm, such as is being developed here off the coast of Virginia. And we can see that wind turbines are essentially streamlined struts. At the top of the strut is what looks like a propeller, and it's a propeller in reverse because rather than putting power into these spinning blades and creating thrust, we're actually going to take the power of the wind from the blades and drive a generator. Okay, we're going to arrange those. They're going to have to be spaced out so that we don't have interference between one and the next. And we're going to raise them up away from the surface of the earth. And we're also going to try and get them away from any kind of protuberances from the earth, such as mountains, such as buildings, anything that would disturb the wind around the turbine. So let's talk about the basic process, first of all, for engineering wind turbines. The energy generation cycle starts with the wind turbine blade. The blades are going to turn a shaft. That shaft is going to pass through some transmission, some gears, for instance, and it's going to drive a generator. That generator then will take the power through a transformer. The transformer will then distribute it through a distribution system, and that'll eventually get to homes and businesses. So that's the basic process for generating energy using only the wind. So I mentioned that the wind turbines are located high above the earth. Well, if you study the flow of air over the earth, or actually the flow of air over any surface, you'll discover that due to friction, the flow near the surface is actually lower in velocity than it is away from the surface. This concept is known as a boundary layer, an area where energy is reduced. And this is something that you'll learn about in fluid mechanics. Okay, that's our first course that we're identifying in mechanical engineering. We also talk about this in aerodynamics as well, And this is the reason that wind turbines are mounted high above the earth, because we'd like to get those blades into the higher velocity flow of air so that they can extract more energy. So let's look at the actual wind turbine machine element design. So the diagram that you see at the right is showing the 3 turbine blades connected to a hub. Then that hub is spinning a main shaft. The main shaft then passes to a gearbox, and the gearbox then drives a generator. And they're all spelled out there with the red leaders. At the far right of the wind turbine, you see there's some instrumentation here. There's actually a little vane that tells us what the direction of the wind is, and there's a little spinning anemometer here that gives us the wind velocity. So based on those measurements, we're actually going to adjust the pitch or how the blades are facing the wind about this bearing labeled as the pitch bearing. So we actually twist the blades based on that reading. We're also going to rotate the turbine housing, the whole thing here, which is known as a nacelle. We're going to rotate that on a bearing that sits on top of the streamlined pole. So we're going to point the turbine into the wind direction. And the problem is that the wind is actually varying, right? The direction's not exactly fixed. So we're going to use some sophisticated algorithms to look at the wind data, to average it over a period of time and say, okay, the mean wind is coming from this direction, and then we'll turn the wind turbine into the wind. Okay, so all of these elements that you see in here that have been identified, all these bearings like the pitch bearings, the main shaft bearing, the actual main shaft itself, the yaw bearing for turning the nacelle, the gearbox, the generator, these are all mechanical elements that have to be designed by mechanical engineers. They all have to withstand certain loads and rotational rates. And we're going to understand how to go about this by studying courses like dynamics, where we look at moving bodies, mechanics of materials, where we look at the strengths of materials, and we look at how the materials will deform and deflect. And then mechanical design, where we pull all these things together and understand how to specify a bearing. Okay. All right, let's focus on blade aerodynamics for a second here. So here we're looking down on the turbine. This is the axis of rotation of the turbine. We can see a turbine blade, or one of these wing-like devices that's sticking out. And we think about the design of the actual blade. It looks exactly like a wing, except that it's twisted as we move away from the hub out to the tip. So much like a propeller, if you've looked at a propeller before. If we were to cut a section, just take a saw and slice right through the blade, we would see the diagram that I'm showing you at the right, a blade section. And if we were to add the relative velocities of the spinning blades and the flow of the wind over the blade, we would end up with a wind direction shown by this blue arrow labeled as W. And for those of you that have studied vectors, this is the vector sum of the oncoming wind and the rotational speed of the actual turbine blade. So now we have this airfoil section, looks like a wing, right? And flowing over it. What does it do? It generates a force. So we get 2 forces, one called the force of lift and one called the force of drag. Okay, so the force of drag is going to be identified as parallel to this relative wind direction, force of lift perpendicular. Those forces act on the structure of the blade. And so now that we have a prediction for what those forces look like, we can actually size the blade structure to resist these loads. So to understand where these forces come from, we can again turn to fluid mechanics and also aerodynamics coursework. Again, both courses in the undergraduate curriculum. All right, so we know what the loads are. How are we going to size these blade structures? Okay, well, we're going to again look at our coursework. We're going to go to material science to understand how materials will react. We're going to look at mechanics of materials to understand how much deflection will occur, how much stress and strain we will see in the actual design. So one of the things we worry about is how do the blades deflect when they're under load? And here is a computer model showing one blade, okay? So as we move out from the root, this is where the blade is spinning from its hub. We move out to the root, from the root rather, to the tip of the blade, we see that the deflection increases. Makes sense, right? It's like standing on a diving board. Where the diving board's mounted, it doesn't move much, but if you're standing on the end of the board, it deflects a lot. So it's the same thing here with this wind turbine blade. Most of the deflection is going to be evident as we get out towards the tip. So we're actually predicting this deflection using a computer-aided model. We're putting the geometry into the model by using computer-aided drafting. Okay, so the finite element method is what we call the method of modeling the structure. And again, that's a course in undergraduate curriculum, as is computer-aided drafting. Okay, so now we know what the blade has to look like. We've selected some structure. Now we actually have to build it, right? So how are we going to get that very streamlined shape of the blade? Well, we're going to actually mold it. And at the right here, you see a mold. And so we've got to define two halves of the blade. And here you see one half, and you see all the engineers standing around it here. And what we do is the material that we'll select is actually a composite material. So we're going to choose a fabric, and we're going to hold the fabric in various layers using a resin. If you're not familiar with that technology, it's the same thing that's used to build most of the boats that are on the water today. Also, to relate back to earlier in your childhood, you might have made paper mache before, right? So you might have used fabric or newspaper and strips and then bonded it together with a plaster of Paris. That's a form of composite because you've got some basic structure and you're binding it together, right, with a resin. That's what we're doing here. We're choosing a very strong fabric like carbon fiber, Kevlar, and fiberglass. We're laying it up in the mold, and we're introducing a plastic resin to it in a liquid form, which then hardens. And the basic structure that we make in the molds looks like this. We'll have a top half and a bottom half, and then we'll join it with some structure that runs along the axis of the blade. Here we're labeling these as shear webs. And here's the top and bottom half, which has an adhesive joint at the trailing edge. Okay, and so now we've built this hollow structure, which is very strong, that we're going to use for our wind turbine blade. And the actual finished blade is shown in the center picture here. You can see the structure in the center here where we labeled the shear webs. This actually only has one. And you can see the material after it's hardened in the mold and been taken free of the mold. And here you see the airfoil shape because it's been cut through in order to show us that. Okay, so that was my my example of wind power. Now we're going to switch to nuclear power and talk about how mechanical engineers are involved in the production of nuclear power and the machinery that supports it. Okay, again, we'll look at the classwork that's relevant in mechanical engineering. So here is a nuclear power plant, and there's a kind of a cartoon drawing here at the right that shows us how it works. Here on the far left, we see in green, this is where we have atomic fission taking place. This is our reactor. We've got some shielding insulation around it. Passing through the reactor, we have water in pipes. Hot water under very high pressure then is fed into a vessel. We're going to call that the steam generator. It passes down through a spiral tubing, and as it passes through this vessel, it transfers heat to water generating steam, and then it is returned back to the reactor vessel by way of a pump. So this is a closed circuit, right? There's no exchange of water between the water that's being used to generate steam and the water that is used that goes through the nuclear reactor. So once the steam is produced in the steam generating vessel, then it passes into a turbine generator combination here. So the turbine is going to take this high pressure steam and spin up a wheel similar to the wind turbine, but with different different medium being the steam. Same thing again, we're going to have a series of bearings, a common shaft. We're going to drive a turbine, drive a generator that makes electrical power. We're going to go out to transformers and electrical switchyard and send the power out over transmission lines. Okay, so two closed circuits. The one I showed here is used for passing very hot water from the reactor through this heat exchanger known as a steam generator. The second is the steam itself passing through pipes into the turbine generator combination, then into what's known as a condenser to return it to water, and through a pump again and back into the steam generating vessel. So we have a couple of pumps here, and we also have a turbine generator. We have pressure vessels. These are all things that mechanical engineers will design. So just as one example of that, let's look at a pump. Okay, so on the far right here, you see a pump. This is a specialty pump that is driven by a shaft here. And if you look at the yellow area, yellow and red elements here, these are actually passages through the pump where we're increasing pressure as we go through a series of impellers. So you can think of an impeller, think of a washing machine, right? A washing machine has that big arm device that bangs your clothes around inside a drum. That's an impeller. This is a close fitting impeller here in yellow. And this is actually used to spin in a continuous circle and push water through a pump in order to increase the pressure. So that's what we're seeing here, mechanical pump. So fluid mechanics is going to cover the sizing of these pumps, how to pick the right pump for the job. The actual thermal cycle that we saw, if we go back a slide here, the thermal cycles that we see passing through the reactor into the steam generator and also the steam generator into the turbine, those are going to be covered in courses in thermodynamics. And we have 2 courses in thermodynamics that will talk about that. The actual passing of heat between a hot water pipe under pressure and this vessel that contains the water that turns to steam is covered in a class called heat transfer. So you talk about the design of these heat exchangers. Okay, my last example then is one for propeller performance, and this is one that I've personally been involved in. So we're going to talk about how do we actually predict the performance on propellers and how do we measure that performance more specifically using instrumentation. Okay, here you see a computer generated image from computational fluid dynamics. It shows an airplane with rotors on the front here that then create this vortex flow or spiral flow behind the propeller, behind the airplane in the wake. So let's look at an example. This is the aircraft that we worked on at ODU. This is known as the Grease Lightning or the GL-10 aircraft. It's an interesting UAV or uninhabited or unmanned aerial vehicle. It has 2 wings that tilt. The wings have a lot of propellers on them, known as a distributed propulsion system. They have 10 electric motors driving them. And the airplane, with its wings tilted, as you see in the top image, is able to take off vertically and land vertically. So it essentially can go straight up and down like a helicopter. Then once it's off the ground in takeoff mode, it can tilt the wing and it can go into forward flight. And that's what's shown in the image at the bottom here. This is the forward flight. So in forward flight, instead of using all the motors, they feather the propellers, or the propellers fold back. And now we're only going to drive the airplane with the wingtip propellers here, which have some advantages in efficiency by driving it from the wing. So we'd like to understand what kind of performance can we get from these propellers. And the project we were involved in was to measure this performance. So here's one of those propellers in the Old Dominion University wind tunnel. You can see this blue bulb-like device behind it. That's what we're going to talk about. That's the performance measurement instrument for the propeller. To understand this performance, we need to measure several quantities, but the ones we'll talk about are the force of thrust and the moment or the torque that you get from the rotation of the blades. We also need to know about the rotational rate of the prop to get the performance, and we need to know what the airspeed is in the wind tunnel. And the airspeed in the wind tunnel is simulating the airspeed we get when the airplane passes through the air. Here, instead of the airplane passing through the air, we're going to pass the air past the airplane, if you will, by running airflow through a closed duct under controlled conditions while we hold the airplane, or in this case, the propeller, fixed. So here's what the test stand looks like. This is a CAD model drawn by one of my students that shows that interior of that blue test device that I showed in the wind tunnel. Here's a little picture of it actually built. And here are the salient features of it. We have, again, around the outside here, we have a composite shell, so similar to the way we made the wind turbine blades. We have bulkheads, which are structural supports. They're shown here. We have the actual measurement instrument that's going to measure thrust and torque. That's called a load cell. That's shown here. And then we have the motor up front here, which will be driving the propeller. Okay, so that load cell that I showed here in the model, the computer model in aluminum, okay, is shown here actually manufactured. So this was built in the shop at Old Dominion University, and it's essentially a rectangular section that has been hollowed out in the center, and then all these different little thin beams machined into it. There are two sets of beams we're interested in. One is the one shown here, which we'll be using to measure thrust. And then there are 4 beams over here, which we'll be using to measure torque. And what we do is we relate the deflection of these beams to the force being applied to them. So again, a computer model shown here on the right is used. We apply these forces virtually. Thrust is the red arrow, torque is the blue rotational arrow. And then we look at how the structural model deflects. And this is highly exaggerated. They actually only move a few thousandths of an inch, right? Or about the thickness of a human hair. This is exaggerated just to show which direction they're moving. Otherwise, you don't even see it if it's to scale. So to make an instrument then, what we're going to do is go into our electromechanical devices, right? Our mechatronics understanding. We're going to take a little device that is built up of a wire grid, and I show you that here on the right. So we follow an electrical connection into the grid. It goes through a large serpentine, kind of like a river meandering through a delta, right? And then back out to another electrical connection. This is bonded to a piece of material that is very flexible. Then we'll glue that to a piece of metal. And what happens is as the metal deflects, as we see here, we have a gauge bonded in the area where it deflects the most. And the wire now will change length. And as it changes length, it changes resistance. So we'll connect that wire then to a special circuit. And as that wire changes resistance, we can measure a change in voltage. And that becomes the signal from our instrument. So we'll use mechanics and materials to help us predict how much it'll deflect, and our knowledge of electromechanical systems to help us decide what strain gauge to use. So here's the finished device I showed you. Here is the strain gauge shown in an enlargement, right? And that is the device I showed in the previous slide. So now what we have is an instrument that when we apply a thrust to it by way of the propeller, we can actually measure a voltage. Okay, you say, great, we have a voltage. It still doesn't really tell us anything. And you'd be right, because now we have to go to the computer. So the computer is going to allow us to digitize this voltage, right? And then we're going to write a program, another part of our mechatronics understanding, right? The programming aspect and the understanding of computers. We'll program the computer then to display and file all these quantities that we measure in the wind tunnel. So this is an actual screenshot. Here you see the thrust and torque being measured on a propeller. Here's the speed that the propeller is rotating at. And this is our actual, we call it a virtual instrument that helps us easily file and understand these propeller performance quantities. Finally, we'll report results. And here is a plot now, or a graph of the thrust plotted on the vertical axis and the relative air velocity here on the horizontal axis. And you can see as we go faster and faster with the propeller, think of this as flying the airplane faster, the thrust diminishes as we go, right? And eventually we reach a limit where we no longer have any thrust. So this is one of the limitations on how fast we can go on an airplane. When we run out of thrust, right, and we can't oppose the forces of resistance, which we call drag, we can't go any faster. So to understand this well, we need to not only understand the points that we've recorded here, but we need to understand what is the uncertainty in all of those points. So we don't really have one thin line answer there. We have a fat line that is between the two dashed orange lines, a little bit of a cloud, if you will, around our answers, saying that, well, we have a general idea of the average value, but it could also be a little higher or a little lower. We call that uncertainty. So that's the last piece of our puzzle here, and that is understanding statistics. Okay, so I only have just a minute left here. I'll talk a little bit about expectations. These are some of my students that built the airplane that you see at their feet. We took them to an international competition and flew against a number of different schools from all around the world. And their whole design was to take some of the concepts I've shown today, design and build an airplane that was powered by an electric power plant and carry as much payload as possible, and then be able to fly, take off, and land the airplane without it breaking. All of this with an airplane made out of balsa wood. So that was a great project. And that's one you could be involved in as a senior. To give you an idea of what kind of salary you could expect, here's the national average salary in the USA for a fresh out graduate in mechanical engineering. So about $59,000 a year. And that ranges anywhere from $35,500 to $85,000. If you look at the average mechanical engineering salaries everywhere in the US for anywhere from a fresh out to a very seasoned engineer, they're going to range somewhere between $60,000 and $120,000. What will you be doing? Well, this is a breakdown of what people are doing in the USA. So supporting architectural engineering and related services, about 20%, machinery manufacturing, about 14%, some form of transportation equipment manufacturing, about 11%, computer electronic products, 7%, scientific research and development, like the propeller work, 6%, and then all kinds of other things, the other 42%. All right. And I want to thank you for listening to me today. And these are some resources at ODU that are available to you. You can find them on our website. And you can see those 3 pictures at the bottom are capstone senior projects that we have here at ODU.
Thanks, Drew. That was great. So I see many questions in the chat box, but before we get to those, I'm going to let 2 of our current mechanical engineering students introduce themselves. So if you have questions for students, you can add those to the chat box. So Sydney, if you could introduce yourself, please.
Sure. My name is Sydney Fletcher. I'm a junior mechanical engineering major at ODU. I'm the current president of the Engineering Ambassadors. I'm a member of SWE. I'm on the student council for the Makerspace. I am in the marching band, and I work for the College of Sciences Machine Shop.
Thank you, Sydney. Mystique, could you introduce yourself, please?
Hello. Oh, excuse me. I'm Mystique Owens. I am a recent alumni. I graduated this 2020. I guess I'm no longer in these clubs anymore, but I used to be the vice president of the Engineering Ambassadors. I also used to be the operations manager at the ODU Makerspace that just came up. I suggest you guys all visit it. I was in SWE. I was in the National, well, I am still a National Society of Black Engineers member. I was in a couple other things I cannot remember right now. And since I just graduated, I have a couple of job offers lined up. I'm trying to get into something that has either manufacturing related or research and development. And the job offers I have, they're looking pretty good. So I'm just still trying to decide, mainly based on distance. I don't like growing that much. So I'm a very proud monarch. And even though I'm fresh out, I can still have a lot of information to impart.
Thank you, Mystique, very much. So if you have questions that you'd like to ask a graduate of mechanical engineering or a student, please go ahead and put those in the chat box. And then Drew, I'm going to go back. I have several questions for you. The first question is from Brian from Medan, Indonesia. And he says that he is a sophomore in undergraduate aerospace engineering. And he's wondering, will it be easy for him to get a job as a mechanical engineer directly, or does he need to take some mechanical engineering classes?
You're an aerospace engineer and you want to do a mechanical engineering career. Is that what you're saying? Yeah, I think that they are very closely related. Obviously the aerospace spin, if you will, is going to be more oriented towards flight vehicles, space vehicles, etc. But you learn some of the same things, most of the same things So I would say yes, you would be able to get a straight mechanical engineering job. Yes.
Thank you. So Hector from Mexicali, Mexico, has stated that he actually is studying for a career in mechatronics, and he does agree that you use both digital control systems and control electronics. But he's really interested in producing or designing robots that are autonomous. And he's asking, what type of coursework do you think is important for that type of career path?
Well, I think if you're a mechanical engineer, you're well poised. It's important that you understand mechanisms. It's important that you understand dynamics, kinematics, things like that. Machine design is very important. A robot's another one of those systems that sort of has everybody involved, right? Everybody, but even fluids sometimes. I was going to say not even fluids, but even fluids can be involved because you have things like lubrication of bearings that involve fluid mechanics. So mechanical engineer is going to be well poised with the full undergraduate suite of courses, particularly if you have mechatronics. So I would say if you're interested in robots, you're doing all the right things.
Okay, and then this kind of goes back to that original question. The question is, what's the difference between aerospace and mechanical engineering? You said they're very similar, but what about the career opportunities for each?
Okay, well, the difference I kind of highlighted in that previous question, right? Whereas aerospace is a little less broad in that we're looking at flight vehicles, we're looking at satellites, we're looking at space vehicles, right? Versus looking at everything. So they're probably not going to address manufacture of washing machines, for instance. But in terms of careers, there are absolutely careers available to both. And one of the things that we do at Old Dominion, for instance, is we don't have an undergraduate aerospace program. We have a graduate aerospace program. So what we have as a prerequisite for that is that you have an undergraduate degree in mechanical or electrical or other engineering disciplines. So you can get from mechanical or electrical to aerospace. And if you're aerospace now, you could do the same thing. You could also get to mechanical if you wanted to and get a master's in mechanical. As far as what are the expectations for undergrads, I think they're very good in either one of them, either field.
Great, thanks. So Paulina, also from Mexico, asked the question, how do generators turn kinetic energy into electricity?
Okay, so the shaft that, like for instance, the wind turbine, the shaft is spinning, right? And what you have is you have a series of magnets and coils. And if you've looked at electromagnetics and physics, and if you haven't, you will, okay, when you're studying engineering, and physics being one of the first courses that you take as a freshman, you'll learn that this electromagnetic effect allows you to generate electricity. So you're passing the magnets through coils, that's generating electricity, and that if you do that with a rotary machine, then you can actually get a continuous flow.
Great, thank you. So I have a question for the students, and this is a question from Mexico. And the question is, how would you describe your experiences as a female engineering student and graduate?
My experiences?
No, that's for Sydney.
It's like, what?
Going into college, definitely that's all you hear about is that, like, you're gonna be in the minority. You know, there's not gonna be a whole lot of females. ODU specifically, I participated in a program that was specifically geared towards giving female students an advantage. So we got to live together for a couple of weeks and meet each other and learn about the industry before school started. There's a lot of really good resources out there, like SWE and a lot of other organizations that are dedicated to helping you find those other female engineers and build that community. It really just depends on also your personality. Being on drumline like I am and being engineering, I'm kind of just surrounded by guys all the time. So it's not really weird for me, you know, because I've been doing drumline for years. So it's like, you know, being in a group of all guys, that's not really new to me, but I knew some other people who it was kind of a shock. You will notice, at least I've noticed, that if you're in a class and another female engineer has a question, they're more likely to come up to me, or I'm more likely to go up to them and ask the question than one of the guys, because it just feels a lot more comfortable asking a fellow female engineer. It just feels a little bit more comfortable. But the most important thing is definitely building that community and the support system, and knowing, you know, that you have people to go to talk about any of the difficulties you've had. And just being there for your fellow females and everything like that.
Thanks, Sydney. Mystique?
So when I started the engineering program, I kind of went in a little bit blind. I didn't realize SWEET existed, or there were other, you know, female groups on campus that was geared to, you know, to, I guess, nurture this STEM girl. I kind of just went in like, oh, I'm just diving in. It's cool. But I came from a high school that was also pre-engineering based, so I was used to being around majority male classmates. I remember my first engineering course I ever took, which was back in high school. I was one of two girls. At the time, I remember feeling scared. And I'm not thinking that I was going to get like beat up by a boy or anything, nothing like that. I just felt like I was going to be outnumbered, or I was outnumbered, and I thought that I guess the mental attitude of the class would be different because I was the only girl in there. And it'll be like a boys' club. However, these, like most, 9 times out of 10, I have rarely had a bad experience with my male classmates. They've embraced me as like a sister or as another friend. And it was probably, I made some of my closest friends with, you know, the guys I've connected with. And there was never a time where I felt like, you know, the guys were like, oh, she's a girl, you know, get her out of here, boo. It was, you know, no one really said anything except for like the times when they were like, oh, you kind of borrow your water bottle. It's like, oh, there's lip gloss on this. It's just, that was like one of those determining times that they kind of remembered that I was a girl. But so I wanted to say that to say, for anybody who felt scared like I was when I was a freshman back in high school, don't. They're not scary. It's not a scary thing to be. In fact, it is a very eye-opening experience to be a, you know, a small minority in a set of people that do care and have the same goals as you, because you get a what's it called? I guess a vantage point that you wouldn't have really thought about, or you haven't really thought of some your own, like I guess personal bubble of, you know, being a woman. And then, you know, in your environments, like being in an English class, there's mostly a lot of like women in those type of classes, women going to a male dominated class. The vibe is different, but it's still a good vibe. I liked it. The only time there was I guess a mild issue was when I first entered my engineering job area, and that was interesting. But there was also other factors that contributed to that. Being that I started my first engineering internship as a sophomore, and I kind of went in with like the big doe eyes, and not that I looked like a target or anything, but they can tell I was really fresh out the market, and a lot of the older engineering supervisors were like, oh, you know, she doesn't know how to use a drill. And I actually did. So it took a lot of, I guess, tenacity to be able to, I guess, not be afraid to stand up for myself. And I want to say I was not bullied. It was more the fact that it was a, you know, there's a new young girl entering this field with men that have already been here for 20 years. And I wanted to make sure that they knew that I meant full business. And I wanted to be here to experience engineering as a professional and not to baby me. So, and I thought that was an important message to get across to my peers. And after working there for a couple of years, I became a very respected intern. I got some of my best experiences there, and it helped me get a new job. So I think that's it.
Great, thanks, Mystique. So Drew, the next question is for you. So do you know if there is more military or private industry aerospace design work? And is it easy for an international student to work in the U.S. aerospace industry? Drew, you're muted. If you could unmute. Drew, we can't hear you.
I think you muted me, Carol.
Sorry.
Yeah.
So we can hear you now. You're unmuted.
Oh, you can. Okay.
Yeah.
I'm not sure how that happened. I didn't mute myself. Okay, so let me remember the question now.
Okay, so the question is in the aerospace industry, is more of the design for military aircraft or private industry aircraft design? And then is it easy for an international student to enter the US aerospace industry?
Okay, so I don't know what the percentages are, military versus civilian, but they're both very active. And if you count all of the small unmanned aerial systems right now, there's a lot going on, both in the military and the commercial sector. As far as a foreign student, you can have issues getting a job with military contractors if you're not a green card carrying citizen, right? So that can be a problem. There's definitely a problem there. But on the civilian side, it's a lot easier. Okay.
Okay, so I have a couple questions about strain gauges. And the first question was, so the strain gauge helps to know how much pressure is on the mechanical system when it's exposed to a force, either in the case of the propellers.
Yeah. So okay. Is my slideshow still active?
Yeah, you can go back to that slide.
Okay. Yeah, let me go back to that slide and I'll try and explain it a little more. So yeah, so if we think about what we're doing, we're applying force to a mechanical structure. So the structure is shown here. And the idea behind this structure is that we try and make it compliant, meaning it'll bend in the direction of applied force, but it won't bend in any other direction. So in this case here, we're applying thrust, which is along the axis of the instrument, as I've shown with the red arrow over here. These groups of thin beams I'm showing in aluminum over here are being represented by the computer model in the section I'm orbiting now. So what happens is when you put the force on there, these thin beams are going to bend, right? I think my analogy was the diving board, right? You're standing on the end, and so the beam bends. So when they bend, that deflection causes the metal to actually stretch or strain, if you will, at the surface. And we bombed a strain gauge right in the area where it is changing. And that's what I tried to show here. Okay, so here's one of those strain gauges bonded to the piece of metal that's bending right at the area where it bends the most, okay, or where the strain is the greatest, I should say.
Thank you.
Yeah.
So Jorge from Maryland has a follow-up question to that. He asked if they were going to have access to software through this program for strain simulations, and I think the answer to that is no. But he also asked, do you recommend software that can be used for strain gauge simulations?
If you're trying to do what I'm showing here, okay, what I'm showing with the blue computer model here, so that you can understand what sort of strains occur, so you can know where to mount strain gauges. That would be the usefulness of software, I believe. If you want to do that, you can do that with many software packages that are computer-aided drafting. They usually have an add-on that allows you to do this kind of analysis, which we call finite element methods. So if you have Autodesk Inventor, or if you have SolidWorks, they'll allow you to do this.
Okay, thank you. So Daniela from San Lorenzo, Puerto Rico, asked if you could recommend some papers or books to better understand the job of a mechanical engineer in manufacturing for a high schooler.
Wow, that is a big one. I don't have anything at the tip of my tongue right now, unfortunately.
So Drew, does the American Society of Mechanical Engineers provide that information on their website? Because I know the American Society of Civil Engineers does, so maybe that's a resource.
There definitely is information there. Yes, there is information. I haven't looked at it in quite a long time, but there is ASME. If you just go into Google and say ASME, mechanical engineering, jobs, employment, or something like that, they'll describe what you do.
I can
Great.
add to that a little bit.
Yeah,
Professor.
please. Sydney.
So
Yeah.
I'm a member of ASME, so I can confirm. But when you become a member of ASME, they send out EAs every month. So it's mechanical engineering. Each one has like I have one about COVID response. I have this one's about startups. This one's about colleges that are doing cutting edge research. So when you become a member of organizations like ASME and other organizations, they'll pump out a lot of literature your way. So that's definitely ASME would be the resource that I would recommend as well.
Great, thanks, Sydney. So another question is specifically about the ODU graduate program in aerospace engineering. And the question is, do you offer programs or classes in orbital mechanics, propulsion, and spacecraft design?
The first two, we definitely offer the first two. Spacecraft design it's not a formal spacecraft design class, but we do talk about those topics for sure.
Okay, and then here's one from Yaha from Orlando, Florida, and he says, I'm interested in mechanical engineering, specifically with transportation, such as aircrafts or cars, and I like the science aspect of it, but I am unsure about the math component of it in terms of interest. Should I pursue it in college as a major?
Well, I think the way I like to talk about mathematics with engineers is you need to think about it, understanding mathematics kind of the way you would understanding the learning of a musical instrument. The mathematics is kind of the scales, the notes, the chords that you learn before you can actually play or sing a song, right? So you need to have some fundamentals behind you, and that's for engineering. Mathematics, there are scales, right? That's our foundation. And so if you're interested in engineering, you do necessarily need to embrace mathematics. What you'll find is that after you go through a lot of the coursework, once you narrow down a discipline, you'll find out that you'll use just parts of what you learned in your mathematics background, but it is very important.
Great. I'd like to, I'm sorry, go ahead.
I kind of resonated with the student that asked the question. Admittedly, I do not like math too much. As you can also tell, I also have my degree now. So I would like to say that my relationship with mathematics throughout the course, I was more of a theory learner. So even though I kept missing a negative when I would do my simplifications, you can understand when you're doing the math that the theory that is applied throughout the coursework, you can see it fit in like puzzle pieces. So instead of me just trying to, resenting the fact that I was doing my upteenth problem at 3 a.m., I thought of it as, well, in my fluid mechanics class, this lines up with this theorem. And then I could see the same patterns in my physics 1 class, and things started to line up. You even start noticing how, like, in your OD, which is the ordinary differential equations course, it's like once you finish the math portion and then you see how it's applied in the class, it gets almost 10 times easier because you can see where the math and what it is doing. So anybody who's a little, math scared, I do encourage you to go forward with the program, because if you're a logic-based person, this will still make sense at the end of the day. So, and make sure you get a good calculator batteries.
Thank you, Mystique. So we're out of time now. I'd really like to thank Dr. Landman for his great presentation and answering questions. And I really want to show my appreciation to both Mystique and Sydney for being here to talk about what it's like to be a recent engineering graduate and a current mechanical engineering student. We are so excited to have all of you online with us today for this session. There's some questions that we just couldn't get to in the chat box, so we'll try to answer those questions and post those online for you. And again, I hope you have a great day, and I hope that we get to see you again and again in the next 8 weeks for these sessions. Thank you so much. Bye, everyone.
Thank you. Bye.
So Miguel, do you end the session?
Yes, ma'am. I am ending the stream now, and the recording will post soon, and we will provide an edited version of that.
Thank you. And then Drew, I might, if you don't mind, I'm going to put some of these questions in a Word document and maybe send it to you. There's only a few really that we didn't answer. And if, would you mind possibly answering some of them?
Sure, I'll answer them. Yeah.
All right, great. Miguel?
Can I make one comment? Can I make one comment?
Yes.
I thought, first of all, Mystique and Sydney, you guys were fantastic. And one thing you want to say when you both use the word SWE, I doubt anybody knows what SWE is. You should probably say Society of Women Engineers, which is a very important organization because I think it gives people a home. So.
Right, that's a good point. Yeah.
Okay.
Whoops. I didn't even think about it because usually anybody that I talk to is going to know that. But
They know what it
that's
is. Yeah, I know. And I thought to jump in. Every time I thought to jump in, it was a bad place. So I didn't do it.
I was in an interview today, and
Well, you guys did great.
right, it was crazy. And I was like, do you mind explaining the acronyms to me? And they're like, oh, I'm so sorry. So, completely understand.
Yeah, you guys did a great. This was a great program today. So thank you all very much.
Thank you. Thank you for the opportunity.
Thanks, Miguel.